This was supposed to be part 2 from the Yellow Submarine project review. But Michał, so Michał reached out to me saying, "Man, you're crazy," etc. As in, like, there's a bunch of stuff. It's really complicated. It's going to take a lot of hours. Here we go. I mean, I don't really care. I think I think it's worth spending the hours. But what I'm happy is that I just picked that problem totally the project totally randomly, and then it turned out that this is like sort of I opened the box to a completely different type of quantum computing, which is what Xanadu, I hope I'm pronouncing it correctly, is doing apparently. So, whoa, give me a second. Some technical issues here right now. Okay, got to figure it out. So, what I'm going to try to do is I'm going to try to browse a little bit here. I'm going to spend probably 10-15 minutes taking a look at what that paradigm is, and then how is this different from regular quantum computing. Just really try to get to the basics, and then see if we can just surface around the project. Maybe not do a super deep dive into the project, but at least understand how is that different from regular quantum computing. And by regular, I mean what you see in most of the videos in my channel, right? So the gate model that is prominently implemented by the IBM Q Experience guys. And so, well, let's just take a look, see whether that's really. So what is this? It's literally the first time I take a look at this stuff. So that's what I do in all my videos. I don't really check anything a priori. So blah, 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 the future of integrated photonics. Quantum photonic processors will solve today's toughest business problems. Applications, quantum machine learning. Good. Are there any learning materials? Software. Penny Lane, Strawberry Fields, Interactive. So Michał mentioned I should get familiar with Strawberry Fields if I want to really understand the project well. So the introducing the first dedicated machine learning platform for quantum computers. So that's an actual machine learning platform. Okay. So this seems to be really specific, because those seem like gates as well, and it's like a circuit thing, but there's definitely some weird things like FKVR, which white paper, join Slack, built for machine learning, Strawberry Fields Interactive, documentation. Let's take a look at the documentation. Strawberry Fields. Oh, wait a second. Actually, I did check one of these pages. It was what I was doing. I was doing something, and I was checking something during one of my videos from Xanadu, but I think I was not aware that this is something totally different. So features, Strawberry Fields getting started. Gonna skip all that as usual. So continuous. Okay, so that's CV quantum computing. That's what I didn't. I don't know if he mentioned it. So Michał mentioned it in one of his comments or messages he sent me. But so this is basically continuous variable quantum computing. Okay, introduction. That sounds like the good place to start, right? Many physical systems are intrinsically continuous, with light being the prototypical example. Such systems reside in infinite-dimensional Hilbert space. Mr. Hilbert is everywhere, offering a paradigm for quantum computation which is distinct from the qubit model. Okay, interesting. The continuous variable model takes its name from the fact that the quantum operators underlying the model have continuous spectra. The CV model is a natural fit for simulating bosonic systems, electromagnetic fields, harmonic oscillations, phonons, and blah, blah, blah. Didn't understand any of those words, and for a setting where continuous quantum. But I guess what this is trying to say is that this is sort of truly in nature continuous in terms of the way you manage the information. But I mean, really, is it really different than the qubit model? Because in the qubit model, you can also sort of operate in a continuous sort of, I mean, probabilities. So the amplitude in the phase is not that you have zero. Sure, most of the stuff you use are certain states, like the 0, the 1, the plus, the minus, etc. But that's probably okay. So there's a table here, high-level comparison. So you've got Q modes instead of qubits. Okay, and an information unit is 1 bit, and here's whatever that is. Relevant operators, quadrature operators, mode operators. And here I have Pauli operators, the X, the Y, and Z. And you have common states, common states, coherent states, squeezed states. Okay, so now I know where the squeezed things come, because it was one of the things that I saw here in the code, right? Squeeze get. I was like, what the hell is that? Okay. Number states. So you've got different types of states. Okay, common states, and then Pauli eigenstates. Yeah, this is what we know: 0, 1, plus, minus, and then the complex phase thing. Common gates: rotation, displacement, squeezing, beam splitter, cubic phase. Okay. Phase shift, Hadamard, C0, T-gate. Yeah, so those are we're familiar with. This is the first time I see this. Okay, squeezing, displacement, rotation. Common measurements: homodyne, heterodyne, photon counting. Pauli basis measurements. Yeah, so you can measure on the Z base, on the X base, on the Y base. I think that's what it means. Qubit-based computations can be embedded into the CV picture. The most elementary CV system is the bosonic harmonic oscillator, defined with the canonical mode operators this and this. They satisfy the well-known commutation. Whoa. Okay. It is also common to work with the quadrature operators. What the self-adjoint operators are. This is way too abstract at the moment. We can picture a fixed harmonic oscillator mode, say with an optical fiber as a single wire in a quantum circuit. These Q modes are the fundamental information carrying units of CV quantum computers. By combining multiple Q modes, each with corresponding operators, and interacting them with via sequences of suitable quantum gates, we can implement a general CV quantum computation. So the dichotomy between qubit and CV systems is perhaps most evident in the basis expansion of quantum states. So qubit is this and this. Okay, so it's sort of a linear combination of those two things, while a Q mode is this stuff. What? An integral of whatever. For qubits, we use a discrete set of coefficients. For CV systems, we can have so for qubits, we use a discrete set of coefficients. For CV systems, we can have a continuum. The states X are the eigenstates of the X quadrature. With X being a real number. These quadrature states are special states for a more general family of CV states, the Gaussian states, which we now introduce. So our starting point is the vacuum state. Other states can be, that seems like this, the same thing with with regular quantum computing. Other states, I mean regular, it's not regular, it's just the gate model, or the qubit model, let's call it. Other states can be created by evolving the vacuum state according to this, okay, where H is the bosonic Hamiltonian. So here we are again with the Hamiltonians, and T is the evolution time. I mean, at the end of the day, it's not that it's a different thing essentially, it's just it's a different sort of framework, right? I mean, it's pretty cool to see that. It feels like that's really the language level at the same time, right? So it's like when you've got like Python and classical computer, Python, JavaScript, and all this kind of stuff, and then each of them is a bit of in a different nature. I mean, at the end of the day, what they do is they manipulate the same the same stuff down under the hood, and then this is just sort of like a different mathematical framework for expressing the same. It's like you're messing with stuff at the quantum level. That's what everyone is doing. But then the D-Wave people are doing something different. The Xanadu people are doing something different, and then IBM is doing something different. Small quadratic in the operators. For a single Q mode, Gaussian states are parameterized by two continuous complex variables, a displacement parameter and a squeezing parameter. Okay. Let's, as always, that's the theme of the channel, is intuition, right? So I don't want to understand that. I'm not going to understand all that. I just want to gain intuition about that. And I think that shouldn't be complicated. I mean, okay, so you've got these things, and then you've got like a displacement parameter, squeezing parameter, often expressed as these. Gaussian states are so named because we can identify each Gaussian state through its displacement and squeezing parameters with a corresponding Gaussian distribution. The names displacement and squeezing maybe come from the fact that that's what you're doing to the underlying whatever photons. The displacement gives the center of the Gaussian, while the squeezing determines the variance and rotation of the distribution. So many important pure states in the CB model are special states: coherent state, displacement, and squeezing zero, squeezed states. Okay, the displacement is zero, but there's some squeezing. So this looks like those are okay. So dimensions, and I mean those are the parameters, right? So you can displace it or squeeze it, and then okay, displaced squeezed states is like eigenstates. Okay, eigenstates, vacuum state, number states. Okay, so that's just number states, Gaussian states. We talked about Gaussian states. Okay, number states. Complementary to the continuous Gaussian states are the discrete number states, or Fock states. These are eigenstates of the number. The number states are discrete countable basis. People, I'm really not understanding most of the stuff in here. Each of the Gaussian states considered in the previous section can be expanded in the number of states. For example, coherent states have to form mixed states. Mixed states. Mixed Gaussian states are also important in the CB picture. For instance, the thermal state, which is parameterized to the mean photon number. This analogous to the pure states. By applying quadratic order Hamiltonians to thermal states, CB gates. Unitary operations can always be associated with generating Hamiltonians via the recipe. But this is pretty similar. I mean, really, I might be totally wrong, but this is pretty similar to the way that you can kind of express and build any kind of gate in the qubit model, correct? At least there was something like that in a paper. It's like this, like it's e to the something. For convenience, you can classify unitaries in the degree of their generating Hamiltonians. Gaussian gates, one mode and two mode gates, which are so this is 1 qubit and 2 qubits. I guess are quadratic in the mode operators, displacement, rotation, squeezing, and beam splitter gates. These are equivalent. I find it funny how they keep going back. They keep making an analogy with the qubit model, so you kind of understand Clifford group of gates from the qubit model. What was that? Clifford gates. Which ones were these ones? Which ones were these ones? Image will tell us. Non-Clifford gates, Clifford gates X, Y. Okay, you see, with image search, you will always get what you want. X, Y, Z, the Hadamard, SS. Okay, so, gates. You see, e to the minus I pi, whatever. So those are non-Gaussian gates, Gaussian gates, and non-Gaussian gates. So the Gaussian gates are sort of the equivalent to the Clifford gates. Non-Gaussian gates are single-mode gates, which is degree 3 or higher. Who cares about it? Cubic phase gate. These are equivalent to the non-Clifford gates in the qubit model. What a non-Clifford gates. Tell me what are the non-Clifford gates? Maybe I was too optimistic. Non-Clifford gates. Okay, I guess it's whatever it's not Clifford. 2-qubit non-Pauli. Pauli group, this we know. The Clifford group, okay. Any gate from the form, okay. It's not a Clifford gate, okay. Yeah, good. So now then you've got different gates: displacement, rotation, squeezing, beam splitter, cubic phase. And this is what they do. So what I assume in here is, it seems like this is pretty similar. So you basically have got, but this is Gaussian states, you've got displacement and squeezing as parameters. Number states, I don't know. Mixed states, I don't know. Okay. Because basically, okay, beam splitter, blah blah, cubic phase. It seems that those cases just play with those parameters, right? So displacement probably, I'm guessing displacement probably adds displacement, squeezing adds squeezing, whatever those effects are, right? But then, okay, then you've got measurements. Okay, so the Gaussian, non-Gaussian measurements. The Gaussian class consists of two continuous types, homodyne, heterodyne measurements, while key non-Gaussian measurements is photon counting. Homodyne measurements, heterodyne measurements, photon counting. So this is basically what you, okay, so the measurements you can do. But essentially I might be totally wrong, but intuitively that seems like not so much different than the qubit model, but it's like a slightly different. So you've got a bit of different types of states, different things you can play with, and probably that's because you're playing with photons. I'm not 100% sure, but I think that's the idea behind this, right? That you're playing with photons, and that makes it different. Okay. Conventions and formulas. Boom. The nice thing about standards is that you have so many to choose from. In this section, we provide definitions of various quantum operations used by strawberry fields. Measurements, gates. Okay, so here you can actually deep dive into those things: states, Fock basis, vacuum state, coherent state, squeezed state, thermal state, cut state. Displacement, squeezing. So squeezing, I don't know, squeezing, I just like the word. What the? Oh my god. I have indeed opened the app. A box that I don't know if I really want to open. The squeeze gate affects the position and momentum operators. The Fock basis the composition of displacement and squeezing operators was analyzed by Kral, and the following quantity was calculated. Boom. The important special cases of the last formula are obtained when this and this. On the other hand, okay, find this odd as even. To deduce that, zero Blochmesser. What? What is squeezing? Strength S gate. The position and momentum operators. What else we've got? Displacement. We obtain the position and momentum operators. Position and momentum. The matrix elements of the displacement operator in the fuck basis. Someone needs to work on these people so that this is more understandable. Rotation. We write the phase space rotation operator as it rotates the position and the momentum. Okay. Quadratic phase. It shears the phase space, preserving position. Beam splitter. They will transform the operators according to this. Against states 50-50 beam splitter, 2-mode squeezing. It can be decomposed into 2 opposite local squeezers, sandwiched between 50% beam splitters. So, controlled X gate. The controlled X gate, also known as the addition gate, or the SAM gate, is a controlled displacement in position. So it seems controlled phase is addition phase or addition of the second mode. And the position basis. So this, it seems it's basically touching the momentum and the position. It seems like those operators are defined like that. Okay. But maybe what I should do next is I should take a look at some of the quantum algorithms. So maybe what is in other, maybe that helps me understand that loss channel, thermal loss channel. So that's probably the same thing, like the coherence and stuff like that. The compositions, Wilson decomposition, whatever, regular decomposition. So far I don't care about this, but it seems like it's a little bit more complicated in the sense you've got different types of states. So you've got different types of states, and then you've got different gates. Interesting. I'll take a look at what I'll do is I'll take a look at some quantum algorithms in my next video. Okay, and maybe that's going to help me understand a bit more the basics of this, because it can't be that complicated. Really, probably if you want to know the details, it just can't be that complicated and that different from what the other one stuff. Let's see, and then we'll go back to the algorithm, to the project. Actually, I really want to go back to the project. Don't want this to be sort of a tangent. I think it's worth definitely exploring the whole concept behind Xanadu and behind this the photonic, so the CV quantum computing. But my intuition tells me it's just a slightly different model. Cool. Stay tuned for more. I didn't expect that to end up this way.